Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 8. This is modeling a context from a verbal description. So classwork example number 1 states, Christine has $500 to deposit into a savings account. Okay, so I'm going to stop right there. And I'm going to underline the data that I'm looking for. And she has $500 to deposit into a savings account. She's trying to decide between two banks. Bank A offers 10% annual interest compounded quarterly. Rather than compounding interest for smaller accounts, Bank B offers to add $15 quarterly to any account balance less than $1,000 every quarter as long as there's no withdrawals. Christine decided that she will neither withdraw nor make a deposit for a number of years, so she is going to deposit and then just forget about it. Okay, so we need to develop a model that will help Christine decide which bank to use. So we're going to use a table. Okay, so here's my table, and I have at year end we're going to have a balance and how many years we are doing. Bank A balance and Bank B balance we're going to compare. So this is going to be year 1. Okay, so we're going to look at a few years first. Year 1, year 2, year 3, and year 4, and then we're going to calculate the balances for both banks. But how do we calculate balances? Well, there's several things we need to know and remember from prior lessons. Okay, so the first thing we need to know is what we're trying to calculate is the amount of money that we're going to end up with, and that's going to be A. And principal is how much we start with. And we already know that that's right here, that it's $500. And what else do we need? We need to know interest rate. We need to know number of interests times applied per year. Okay, number of times we're going to apply interest. And T is the number of times the period elapses, or T is time in years. So we're going to try to find A. We know P is 500, and we're going to do Bank A first. They're offering a 10% annual interest, so the interest rate is 10%, which is 0.1. And N is the number of times it's going to be compounded, and it's quarterly, so it's going to be compounded 4 times a year. Okay, so T is time. So for year 1, T is going to be 1. For year 2, T is going to be 2. Year 3, T is 3, and so on. So we need the formula, and it is the amount equals the principal times 1 plus the interest rate divided by the number of times per year, all to the n times t. Okay, so if we're going to now calculate the first year, then my A is going to equal my principal of $500 times 1 plus the interest rate, which is 0.1, divided by n, which is 4, because it's quarterly and there's 4 quarters in a year, to the power of n times t, which is simply 1. So if I go to my calculator and put in 500 parentheses 1 plus another parentheses for my fraction 0.1 divided by 4, close that parentheses and all the big parentheses for the 1 plus the quarter, or 0.1 over 4, and that's going to be taken to the power of 4 times 1, which is 4. That will tell us what our $500 will become after 1 year of interest compounded quarterly. and that would be $551.91. Let's round up to the penny. So it's 551.91. Okay, Bank B balance is just going to add $15 quarterly. Well, there's 4 quarters in the year. 15 times 4 is 60. So you're going to end up with $560 at the end of the first year. So if you're only going to put your money in the bank for a year, then you obviously want Bank B. Okay, but she decides, and she's not going to make a withdrawal or a deposit for a number of years. So we're not done here. She's not going to quit after 1 year, so we need to continue. So now we're going to go on to year 2. So year 2, all we would change is this times 2. So now if I go back to my calculator, and if I just hit second enter, it'll bring back my old equation again, arrow over here, and now this is 4 times 2, or 8. And then hit enter, and look how easy that is. 609.20. So year 2, we're going to have $609.20. So this is going to just keep adding $60 every year. $15 a quarter is $60 a year. If I add 60 to 560, I get $620. So after 2 years, I'm still making more with the interest rate. Okay, so let's just finish up Bank B balance real quick. So as you see, we're adding 60. So this is going to be 620 plus 60, which is 680. That's after year 3. And then add 60 to that, and that is $740. Okay. Oops. Why am I putting decimals there? 680 and $740. Okay, so now I just need to calculate this repeatedly, and if I go back and I just hit second entry, and so now year 3, this is going to be a 3 here, so I'm just changing this 4 times 3. Okay, so that's obviously 12. So I go in my calculator and re-enter the thing by hitting second entry, going to the previous function that I entered, changing this 8 to 12, and hit enter. And while I'm here, I'm just going to do it one more time. Bring up that last formula. And this is going to be 4 times 4 this time, or 16. And hit enter. So there's my last 2 values. 672.44. 672.44. And then finally, $742.25. Okay, so as you can see here, Bank B was ahead of Bank A year 1, Bank B was ahead of Bank A year 2, Bank B was ahead of Bank A year 3. But year 4, I made $2.25, or I should say Christine made $2.25 more in Bank A than she did in Bank B. So initially, the $15 a quarter is better than the percentage of 10. But after 4 years, it's better to have a 10% interest rate than it is $15 quarterly, because interest is compounding on top of itself, so then it starts to grow faster. Okay, so now let's just calculate that formula. I can give that formula. So, Bank A, so if I have Bank A, the formula was right here. So let's just call it a function A of t, okay? Amount that we're going to end up with respect to time, equals, and it is going to be 500 times 1 plus 0.1 divided by 4 to the power of 4t. Okay, so there's our equation. Bank B is going to be Bank B with respect to time equals initial $500 plus 60 times the number of quarters. Okay, so there's our two different equations. Now what we could do is try to determine what quarter in year 3 would be the best time to withdraw, but I'm not going to take it that far. But so if we just went out all the years, then year 4 you're starting to make more money in bank A. Okay, example 2. Alex designed a new snowboard. He wants to market it and make a profit. The total initial cost for manufacturing, setup, advertising, etc. is $500,000. And the materials to make the snowboard cost $100 per board. The demand function for selling a similar snowboard is D of P equals $500,000 minus 100P, where P represents the selling price in dollars of each snowboard. Okay, so A says write an expression for each of the following in terms of P. Demand function, number of units that will sell. Well, number of units that will sell would be the 500 or the $50,000 okay, demand, it's right here, demand function is right here, 500 or $50,000 minus $100 times P, where P is the selling price. So if he sells it for $89, that'd be $8,900 for one board. 50,000 minus 8,900, and so on. Okay, revenue, number of units that will sell, which is price per unit P. Well, you're going to take this function here and rewrite it, 50,000 minus 100P. Now keep in mind that's the demand. Revenue is going to be this demand times the selling price. Okay, so the revenue, number of units that will sell times the price per unit P. It tells us right here. Our revenue is number of units that will sell. Number of units that will sell is your demand function. So demand times P. And this, if I distribute the P, I get P times 50,000. I'm missing a zero here. Let me squeeze one in there. So that's going to be 50,000 P minus 100P times P is 100P squared. And then total cost of producing the snowboard. Okay, well this is the total overhead cost. Total overhead cost plus the cost per snowboard times the number of snowboards. Okay, so since this is the total overhead costs plus the cost per snowboard times number of snowboards, so our initial total overhead cost is $500,000. And we're going to add that to our 50,000 minus 100P, that's A. Okay. But we need to multiply that by 100. Which is the cost per board right here. So the initial cost plus cost per snowboard times the number of units that will sell, which is 50,000 minus 100P. Okay, so now we're going to simplify this by distributing the 100. So it's going to be 500,000 plus 50,000 times 100 is two more zeros, so that's 5 million, minus 100 times 10 is 1,000 P. I'm sorry, that's 100P times 100, so that's 10,000. We add one more zero there. 10,000 P. Okay, so 500,000 plus 5 million is 5,500,000 minus 10,000 P. Okay, so that's the total cost. Okay, so we're going to continue exercise 2. We're on part B. This is page 2. B says write an expression to represent the profit. Okay, well, just keep in mind, profit is going to be your total revenue minus your total cost. So in knowing that, if I go back to the prior page, my profit is going to equal, let me write equals, and then I want my total revenue from the previous page, which is right here. So it's 50,000 minus 100p minus 100p squared. Okay, so now profit is this 50,000p minus 100p squared, total revenue, and then it's going to be minus, and then total cost. So again, if I go back to my prior page, total cost is right here. So I'm just going to copy that, bring it over to the next page, paste it, and that will go right here. Okay, so it's coming together now. And if I'm doing this, I need to be careful about my orders here, and I will just put this in parentheses just so we know that that was our other function. Okay, so we need to simplify this. So f of p, we'll call that profit f of p. So instead of saying profit, we'll say some function with respect to profit. So f of p, when I simplify this, is going to equal what? Well, we have 500,000p minus 100p squared minus 5,500,000. Okay, and I want to put this in standard form, a quadratic. So I'm going to put my p squared first. So it's going to be negative 100p squared. And then I do my linear term, which is over here, minus a negative, careful, is plus. So that is going to be plus, let's see, first of all, I need to do some distributing. Oh, here's a p here as well. So we have 50,000p plus 10,000p. So that's going to be plus 60,000p. Okay, did you catch all that? It's this term here, my linear term. A negative times a negative, when I distribute this negative, is going to make this a plus 10,000p. So 50,000 plus 10,000 is 60,000p. And then minus times a positive is minus $5,500,000. So there's my function. Negative 100p squared plus 60,000p minus 5,500,000. Part C says, what is the selling price of the snowboard that will give the maximum profit? Well, this is a quadratic, so keep in mind, if I graph a quadratic, it gives me a parabola, and the maximum value would be my vertex. So there it would be the max. And that's what C is asking. What is the maximum value of this function? So we need to complete the square. Okay, so we're going to complete the square to find the vertex x comma y, the maximum. So what I do is I write f of p equals, and I'm going to use this function here, but I have to complete the square. So I bring my first term out, negative 100, parentheses, and if I'm going to factor out 100, then this is just going to be p squared plus And this is going to be 60,000 divided by 100. So in other words, take 2 zeros away. That would be 600 P plus, and then I take half of this. So I'm going to just leave a space for now. You got to take half of that and square it. Okay, and then I'm going to put the minus 5,500,000 outside. So that's the initial thing we need to do. So half of 600 is 300. So we're going to add 300 squared. I'll just write it like this for now. So you take half of b and square it. And since I did that here, I need to also do it over here. So if I'm going to, remember this is negative, I need to also add it back in so it's still equal to 0, or not, yeah, equal to the same thing. So if I'm adding 300 squared, but it's a negative 300 squared, I need to take away that 300 squared as well. So it's going to be 100, a positive 100 times 300 squared. Okay, negative 100 times 300 squared, positive 100 times 300 squared would cancel each other out. So it's just like adding nothing. Okay, so now I simplify this. Let me change back to blue. And in simplifying this, we get negative 100, parentheses, p minus 300 squared. And in calculating this here, let's just take a look. It is 5,500,000. Actually, what's 300 squared? So it would be 100 times 300 squared. Is 9 million. So we're taking negative 5,500,000 and adding 9 million to it. So now I'll subtract 5,500,000, and that will give me 3,500,000. So this will be plus 3,500,000. Okay, so there's my f of p. Negative 100 times p minus 300 squared plus 3,500,000. Okay, well, if you remember why we complete the square, this term here is my x, this term here is my y. Okay, so that'd be x minus h squared plus k. So the point would be 300, comma 3,500,000. So it says, what is the selling price of a snowboard that will give the maximum profit? And it is $300. If I sell a snowboard for $300, I will make $3,500,000. Okay? And those commas all look a little confusing. So let me get rid of the commas for the 3,500,000. This is my x, comma, y. Okay, in part D, lastly, it says, what is the maximum profit Alex can make? Well, the maximum profit Alex can make is the y value at the vertex, which is $3,500,000. Okay. $3,500,000. Okay. Exercises. Alvin just turned 16 years old. Okay. His grandmother told him that she will give him $10,000 to buy any car he wants whenever he is ready. Wow, must be nice. I paid $900 for my first car and I had to pay for it myself. Alvin wants to be able to buy his dream car by his 21st birthday. He wants a 2009 Avatar Z, whatever that is, which he could purchase today for 25 grand. The car depreciates, reduces in value at a rate of 15% per year. He wants to figure out how long it would take for his $10,000 to be enough to buy the car without investing the $10,000. So he wants to take that 10 grand Grammy gave him and he wants to wait for a 2009 car to depreciate from 25 down to 10, and then he'll buy it. And he wants to know how long he's got to wait to get that model car. Number 1 says write the function that models the depreciation value. What is this? The depreciated value of the car after n number of years. So we want a function that we're going to call f of n after n years. So f of n is going to equal, so what we're talking about is the cost of the car now. That's the initial value, principal, $25,000. Okay, and we're going to depreciate that, so that's going to be 1 minus the 0.15, 0.15, okay, the interest rate to the power of the number of years. So when I simplify that, that would be f of n equals 25,000 times, well, 1 minus 0.15 is 0.85 to the power of n. All right, so A says, will he be able to buy the car when he turns 21? Explain why or why not. Well, after 1 year, then we just go to our calculator, and let's make this really simple and just fill out the table for now and not worry about the rest yet. So I turn my calculator on, and I press clear, and I put 25,000 parentheses 0.85 close parentheses to the power of x. Okay, actually I'm putting that in the wrong place. I'm going to put this in for y equals. I'm going to clear that. I'm going to turn my plot off from a module or lesson 7. Why did that not shut off? Okay, and so there, my plot is off. We're not doing statistical data here. And I'm going to put my y equals 25,000. Okay, parentheses, 0.85 to the power of x. Actually, let me put a parentheses there. Okay, so it's 25,000 times 0.85 to the power of x. Now I'm going to go to my graph. Second graph is table, and then I can enter. Well, after 1 year, it's $21,250. So this $25,000 a year later, reducing in value 15% a year, would only be worth $21,250. And then I go back to my calculator and I enter 2. And then after 2 years, that $25,000 car is only worth $18,063. So I'm going to put that here, 18,063. And you get the idea. 3 years, 15,353. And 4 years, 13,050. And 5 years, 11,093. Okay. And let's see, 6 years. 9,428.70. Okay, so there we have it. Will he be able to afford to buy the car when he turns 21? So remember, he is 16 now. After 1 year, he will be 17. After 2 years, he will be 18. After 3, he'll be 19, 20, 21. He'll be 22 years old in 6 years. Okay. So we want f of 5. So I would say no, f of 5 is less than, or I'm sorry, it's more than, f of 5 is greater than 10,000. It's 11,093. So that's the reason he can't. B says, given the same rate of depreciation, after how many years will the value of the car be less than $5,000? So I'm just going to go back to my calculator, and I'm going to hit 7, enter. That's not less than 5. 8, enter. Keep going. 9, enter. Getting close. 10, enter. Finally, after 10 years, so f of 10 equals, and the amount was $4,921.90. Okay, which is less than $5,000. So it would be 10 years. Okay, page 3 brings us to part C of this question, and it says, if the same rate of depreciation were to continue indefinitely, after how many years would the value of the car be approximately $1? So you would use this function, f of n equals 25,000 times 0.85 to the power of n equals 1. You'd set it equal to 1. Okay, in order to solve this, you would have to get n by itself by dividing both sides by 25,000 and then taking the natural or the log. And that's not something you're doing yet, so we will use the calculator. So I will go to my calculator and I'll go to y equals, and I put it in my calculator, 25,000 times 0.85 to the power of x. And then I hit graph, and I would go to zoom fit, because if you just graph it, you won't see it. So you have to go to zoom fit, so it goes to the function, and this is a exponential decay. And then if I hit trace, then it gives me my x value and my y value. Well, I'm looking for the y value to get down to 1, and right now we're at 4,700 after 10 years. So I'm just going to move my cursor over. This is the best way to do it without using a table. And notice my y is now down to 900. So I have to keep going, and it's scrolling over, so it pauses for a second there. I'm down to $520, $394, $299, $226, and we're getting closer and closer to 1. Okay, down to 130, 98, and I just keep doing this until I get that y value down to near 1. $32, $24, $18, $14, and $10. Now it's slowing, so it's taking longer to get lower. So it's taking longer to get to 1 now. We're down to $2.70, $2.60, $2, $1.55, $1.18, and here we go. There it is right there. So it's right about $1 here, and that is after 62.3 years. So the answer to this question is, after how many years? The answer is 62 years. Okay, number 2 says, Sophia plans to invest $1,000 in each of the 3 banks. Bank A offers an annual interest rate of 12% compounded annually. Bank B compounds quarterly, and Bank C compounds monthly, all at 12%. Write the function that describes the growth of investment for each bank in n years. So I will start off with the f of a. I'm going to call it a of n. So we're taking Bank A, and it's a function in terms of n being number of years. A of n equals initial 1,000 times, and since it's compounded annually, that's only one compound, so you don't say 1, well, it would be 1 plus 12%, but that is 1.12 to the power of n. So there's my Bank A. Bank B would be B of n equals that same $1,000 times 1 plus my interest rate R, 0.12, divided by n, which is quarterly is 4, all to the power of 4n. Okay, and that's going to be the same as b of n equals negative, or 0.12 divided by 4 is 0.03, so that'd be the same as 1,000 times 1 plus 0.03, or 1.03 to the power of 4n. Okay, and then on to C. Bank C, C of n equals my initial $1,000 times 1 plus 0.12. This is compounded monthly, which is 12 months in a year, to the power of 12n. Okay, and that equals 1,000 times, well, 0.12 divided by 12 is 0.01. 1 plus 0.01 is 1.01 to the power of 12n. Okay, so there are our three functions. B says, how many years will it take to double her initial investment in each bank, round to the nearest whole dollar? Okay, so we're going to fill in this table. So I'm going to go to y equals now and clear that. And I'm going to put a of n for y1. So it's going to be 1,000, parentheses, 1.12 to the power of x. X being my variable in the calculator. Hit enter. And now I'm going to put bank B in y2. So that's going to be 1,000 times 1.03 to the power of 4n, or 4x in the calculator. And then finally y3 will be our C bank. So it's going to be 1,000 times 1.01 to the power of 12n in the calculator being x. So there's bank A, bank B, and bank C's equation. Okay, let me go back up to this one. Is there an x there? Just let me make sure. Yes, the x is there. It was just off the screen. Just wanted to make sure. Okay, so now I want to enter this data, and I can quickly do that by going to second graph for table, and I want to enter 1 through 7. So I go 1, 2, 3, 4, 5, 6, 7 is already there. Y1 is my bank A, so over here I'll call this Y1, and I'm just entering these values rounded to the nearest whole dollar. So 1120, $1,120, 1,254, 1,405. Year 4 was 1573.5, 1574. Year 5, 1762. Year 6, 1974. And year 7, 2211. And these are dollars. Okay, bank B, let me switch to red. Bank B is my Y2, so I'll put Y2 here. That's my bank B. Year 1, 1125.5, which is 1126. And then 1267, and so on. 1426, 1605, 1806, 2032.8 is 2033, and 2288. Okay, now I want bank C. I did that in green. That's going to be my Y3. I don't see Y3 here. It's my X, my Y1, my Y2. I just need to arrow to the right to get to Y3. And there's Y3. 1126.8 is 1127. 1269.7 is 1270. 1430.8 is 1431. Year 4, 1612. 1806. Year 5 is 1817. Year 6 is 2047. And year 7 is 2307. Okay, so it says, how many years will it take to double her initial investment for each bank? Well, doubling $1,000 is $2,000, and in bank A, it would be year 7, sometime during year 7. In bank B, it'd be sometime during year 6. And Y3, bank C, would also be sometime during year 6, but probably a little sooner because that's a higher interest rate. Or not a higher interest rate, but compounded more frequently. Okay, part C. Sophia went to bank D. The bank offers double your money program for an initial investment of $1,000 in 5 years. Initial investment of $1,000 in 5 years. So my T is time. And we want to end up with double the money. Double 1,000 is 2,000. So I know my A is 2,000, I know my time is 5, and I know my principal value investment is $1,000. Okay, so what we want to do is write the formula and substitute in the givens. So remember that A equals P times 1 plus R over N to the power of NT. A is 2,000. That's what we want to end up with. P is 1,000. And my R is what I'm trying to find. So it would be not R over N, because this is going to be compounded annually, so R over N is not what we're going to use here. Well, it is, but N is going to be 1, so it's just simply R. Hopefully you understand that. So N is 1, so that's just going to be 1 plus R over 1, which is R, to the NT. So it's 1 plus R to the N, and my N is, or my N is 1 again. That's my 1 times T, which is 5. 1 times 5 is 5. Okay, so there's our equation. 2,000 equals 1,000 times 1 plus R to the 5th power. In order to get R by itself, I need to get rid of that 1,000 by dividing by 1,000 on both sides. And divide 2,000 by 1,000 and you get 1, or 2. Divide 1,000 by 1,000 and you get 1, and you get 1 plus R to the 5th power. Okay, so now what I need to do is, to get rid of this, is I need to take a 5th root of both sides. So if I take the 5th root of both sides, then I get the 5th root of 2 equals, and these all cancel, leaving me with what's underneath, 1 plus R. Subtract 1 to the other side, and we get the square root of 5. Oops, undo. We get the square root of, or 5th root of 2 minus 1 equals R. Okay, so if I go to my calculator and I take the 5th root, so you go 5, math, number 5 for the variable root, so it's the 5th root of 2, enter, is 1.1486983 blah blah blah. So it's going to be 1.1487, I'll round 4 decimal places, minus 1 equals R, and then when I subtract that I get 0.1487 equals R. So R is approximately 15%. Actually it's 14.87, let's leave it at that. So R is approximately 14.87%. So you need 14.87% interest compounded annually to double your money in 5 years. Okay, page 4 brings us to the end of the lesson. Review the lesson summary and go to your problem set.